Hey, I'm Dmitri. Nice to meet you. Today I'm going to talk about Mysticeti. I'm happy to announce it. Uh, this talk is going to be a little bit technical. If you have questions, don't hesitate to raise your hand, interrupt me. I have two engineers here, Rune and Tassos, who've been implementing it. So with any hard questions, I'm just going to redirect it to them. Rather than that, if there is one thing that I would like you to remember from this talk, is that this year we are going to change consensus. We are going to move to a completely different algorithm, a completely different implementation. The new algorithm and the implementation are faster, cheaper, simpler, more efficient, custom built for Sui. And the great number that we succeeded to achieve is that our consensus commits right now are less than 400 milliseconds in a mainnet-like environment. So let's get to the point. What we are going to talk about now is, in general, I will try to explain how we are thinking about speed. I will try to make a case that the most important thing for speed in our case is the protocol, and the most important piece of the protocol is consensus. I will then try to explain the consensus landscape and the reasons we chose the DAG-based consensus. And then finally, I will move on to explain how Mysticeti is solving some of the latency issues that we used to have with the DAG-based consensus. So with that said, let's go to the Sui speed. In general, as you could have noticed, talking about speed becomes a little bit noisy. It is unfortunately sometimes used in a lot of marketing materials. It's hard to do apple-to-apple comparison. When someone is saying a number, 300 milliseconds, 500 milliseconds, 2 seconds, it's hard to understand what they mean. So at very high level, one could talk about the block time. Block time is somewhat a proxy of the amount of time that it would take for you to learn the results of the transaction. There are no guarantees of finality. It could be that that is going to be reverted. And then it really depends on how adventurous of a client you are, how long you want to wait. Typically, you require some confirmation blocks. In Ethereum today, it's, as you know, like 2 epochs of 32 slots. In Solana, the official thing is that 31 block confirmations is needed, even though a lot of times you don't really wait for these things to happen, but the cleaner way is to wait. A slightly different way to talk about finality is transaction finality, when there is a guarantee that the transaction is going to be eventually executed, but you don't know the result, which is actually okay in some cases when you're transferring, you can predict the result, but in a lot of cases it's not enough. When you're trying to trade, it's important for you to know whether this thing happened or not. This is why typically when Sui is talking about latencies, we're talking about the so-called settlement finality, which means that the results are final and you know them. This is the cleanest, most reasonable way to think about things. The important thing about the settlement finality is that what matters for the settlement finality is not the lower level implementation optimizations. Lower level implementation optimizations are important. They're typically important for improving throughput. They're typically important when your system is overly utilized. But for as long as there is moderate utilization, the only important thing is the protocol. The protocol is about how many times the validators need to talk to each other. The round-trip time in the wide area network is what? 150, 200 milliseconds. And whatever lower level optimizations you can bring, that might bring you typically less than a millisecond in an underutilized system. So that said, by the way, any questions until now? Otherwise, I feel that, OK, perfect. Thank you. Amir understands. Great. So protocol is important. Let's talk about the protocol of Sui. High level again, we are talking about 3 phases. There is one first phase, which is ingestion. There is the phase of ordering and the phase of execution. Execution is the fastest one. As we said, typically execution maybe 1 millisecond, typically less. negligible for the overall settlement finality. The ingestion part is the stable part of Sui. It requires you to talk to the validators twice. There is the first round where you are collecting the verifications, and then the second time when you are sending the certificate to the validators. So this is the two RTTs. As we said, RTT is maybe 200 milliseconds. So overall, the settlement finality for the owned object transactions which do not have ordering on the critical path, they benefit from 400 milliseconds. This is what you see today with the owned object transactions on Sui. We are benefiting from 400 milliseconds finality. However, for shared objects, there is ordering on the critical path because you cannot start executing transactions that touch the same shared object before you agree on the order of the execution. Makes sense, right? So consensus turns out to be the longest pole for the protocol for the shared object transactions, and this is why it is so important for the consensus to be as fast as possible. Now let's talk about the consensus on Sui. At high level, again, there are two types of consensus. Historically speaking, the first BFT protocol that is somewhat practical appeared in the paper called PBFT, and it was 1999. I guess like half of the engineers of Mysten Labs were not born when the first BFT protocol was invented, and later on it evolved to protocols like Tendermint, which support Cosmos SDK, or Hotstuff, DMBFT, Jolton, and others. So what's special about these protocols is that it's typically driven by a leader. The leader is the one aggregating the votes, doing stuff, sending it elsewhere, broadcasting further, and then we build a blockchain like that with leaders which are typically rotating. Now, the obvious advantage of that protocol is that it is relatively simple to reason about. It is typically can be linear in the message complexity. The biggest problem there is that since you are all trying to leverage leader at every round, whenever you have a leader that is a low performer, your throughput is going to drop. Whenever you have a leader that is slightly behind, the throughput is going to drop. You are sending a vote to a leader, the leader was down, that message got lost, so network utilization is bad. The latencies could be low. PBFT, the standard PBFT, is achieving the latencies of 2-3 RTTs. In Sui, we chose to go with the DAG-based consensus protocols for their higher throughput. What is the DAG-based protocol? DAG is the direct link acyclic graph. By the way, if someone doesn't know something, don't hesitate to raise your hand. Direct link acyclic graph, the idea is that we are decoupling the message dissemination from the information processing. You can imagine all the validators continuously pumping the transactions to each other, and as such, building these blocks that are pointing to each other in a form of the DAG. Now, the trick would then be to figure out how to build a commit rule that would be based on that DAG. Now, the commit rule is some sort of an information processing that is happening independently on every validator, and you can build all sorts of things on top of these DAGs. The good thing is about that whenever the leader is slow, what is going to happen? Nothing much. So maybe the specific block that we would like to introduce is going to be delayed, but it is never going to be lost. The other leader is going to eventually commit something, and once it commits that, the whole sub-DAG is going to be committed. So you are getting almost perfect network utilization. Nothing is lost. Throughput is much less affected by the faulty or slow or crashed leaders. This is why Sui is using it. What we've observed is that our consensus today with the DAG-based that is called Bullshark can achieve hundreds of thousands of transactions per second. We know that it is not going to be our bottleneck. Our bottleneck, for what it's worth, is on the execution and on the writes to the disk. The price that we paid for that amazing throughput and the properties of the DAG-based consensus is that we couldn't figure out how to do it fast enough. So our latency was about 4.5 RTTs, which is less than ideal. And as we said, since the latency of consensus is on the critical path for the settlement finality, we would like to make it faster. And let me introduce Mysticeti. Yes, woo. No, that's a big deal. I'm personally, there's the proudest moment of my life. I'm like very excited about the Mysticeti thing because it is a mastermind of our research and great engineering. It's kind of tricky to talk about BFT consensus protocols. I'm personally coming from the theory of distributed systems. I remember these days, every third paper that is talking about consensus protocols is showing you this funny thing and say like, hey, look at the right. This one is clearly better than this one. This is the prior work. And we're achieving n log n square better complexity of the messages. In fact, in order to fully appreciate it, you need to spend, I don't know, 5 hours reading the paper, thinking through it, and here I'm trying to do it in 10 minutes. So I will still try to give you some high-level motivation, but you will not be able to understand it. I will send the link to the paper, and you're encouraged to read it. Now, what was the problem with the Bullshark DAG-based consensus? The problem is that it is actually hard to interpret these DAGs when you are a validator and you don't know whether you can trust the blocks. If you just send these blocks like that, if you're a validator and you see a block, and remember we are in a Byzantine setup, right? So anyone can lie, and you could imagine that the block that I'm observing is not the same block that some other validator is observing. And as a result of that, it's very hard to build meaningful commit rules. So previous researchers couldn't figure it out. They made a shortcut. They said, OK, let's imagine that every block is actually certified. So we are first sending that block to everyone. We are aggregating the votes for that block. And then when we have the BLS signature for the block, then we can send it. It's a certified block. It's a certified DAG. It's much easier to reason about. But we're paying a price because now every block, every round is 1.5 RTT. I need 1 RTT to collect the signatures and then half RTT to actually send it. Obviously, we want to get to the Mysticeti round, where Mysticeti round is just 0.5 RTT. I just directly send the block. The trick is now it's significantly harder, at least in theory, to reason about that DAG. Every block that a validator is observing here, you don't know whether this is a real block or not until you get some additional support for that. So the way that the Mysticeti is working is that it divides the timeline into waves because we're in Sui. And in every wave, there are 3 rounds. And the first round is about the proposal, the second round is about the vote, the third round is about the certification. I'm now going to hand wave and talk about the happy path. But in the happy path, if you have a proposal, and later on you have a quorum of the support, 2F+1, and later on you have 2F+1 certificates for this support coming from different validators, then in the end of the third round, we can prove that you can happily commit that first proposal. That sounds simple enough. Actually, I asked researchers why it took so much time to come up with this protocol. I mean, I explained it in like half a minute. The real reason that it took them so much time is that there are less happy paths. And whenever you are less lucky, you don't have some of these votes, you don't have some of these certificates, you cannot commit right away. And then there are all sorts of very complicated rules to figure out how to actually decide what and when you are going to commit. It's quite mechanical. In some sense, it was hard to prove. Once it's been proven, when we were implementing it, we needed to build a full-blown testing infra to verify that we've implemented it correctly, just to match the rules of the commit protocols. Now we are crossing fingers that Arun did his job. Thank you. No. If there is a halt in June, this is the guy. Now, talking about the actual latencies, in addition to what I just proposed, the curious reader could have asked, hey, you're now waiting for 3 rounds, but what's next? Like, what if my transaction was not part of that block that got proposed and got committed? Am I going to wait longer? And the answer is obviously no. We are doing pipelining, and we are doing multiple leaders per round. So without entering into details, you can imagine that there are multiple overlapping waves, and at each round, the same block is serving multiple purposes. The protocol is tricky, but the high-level intuition is obvious. Like, yes, you are sending a block. Maybe you could piggyback some additional metadata on it. You could piggyback both the proposal and the vote and the certificate for 3 different consecutive waits. And this way, you are introducing the pipelining. In addition to that, you don't have to have just a single leader who is proposing per round. You could have multiple leaders who are proposing per round. And it's all done in Mysticeti in one great universal commit rule that we are very proud of. Any questions until now? OK, great. If there are no questions, let's move on. Just to recap, the biggest Mysticeti innovation is that we succeeded to figure out the way the commits are working with uncertified DAGs, which was significantly harder, up to impossible, to figure out before. We've introduced the universal commit rule with pipeline commits and multi-leader, which is also great progress, but in all the honesty, we could have introduced pipeline commits and multi-leader in the previous Bullshark-based certified DAG protocol as well. We actually started working on it, and then we figured out that we have the uncertified pass as well. The protocol, the proofs, the experiments are all in the paper. This is the link to the paper. I'm encouraging everyone to read it. The intuition there is given way better than I could have given it in the time that I have right now. Now let's talk about the fun part. The Mysticeti performance. The theory, as we said, is 3 rounds. Mysticeti round is 0.5 RTT. So we can get to consensus commit in 1.5 to 2 RTTs. In reality, it is 2 sometimes, because if you are not lucky and your block was not the one that has been proposed in the round, then you need to wait for another half a round. So 2 RTTs. In practice, we've implemented Mysticeti. We've been running it for quite some time in the internal experimental setup that is mimicking the mainnet environment with the same stake distribution across the globe, running on all the continents, typical 200-ish millisecond round-trip time between the quorum of the validators. And with this setup, we succeed to achieve 390 milliseconds of consensus, which is way better than we expected. We never could have anticipated that we could achieve that, because as far as we know, this is the fastest possible thing ever. No one has ever achieved this type of settlement finality. No, and this is a big deal. Like, we were very excited when we saw that. Client end-to-end latency, if you remember, there was the ingestion piece and the ordering piece. Now, the ingestion piece is still there. It's 2 RTTs. So we are paying, and we are overall getting about 640, 650 milliseconds, P50 in the local setup. Now, there is a caveat here that sometimes the settlement finality are not directly translated to the DApp experience. I'm not sure how many builders we have here right now, but typical DApp that is using the SDK that is not fine-tuned is doing some pre-submission RPCs, doing the actual transaction, and then doing some post-submission RPCs. And this is the real user experience. We are working on the SDKs to improve on these things, to add memoization, to bring back the data from the validators to the SDKs, to streamline it as much as possible, so that in the end of the half, we hope that our SDKs would be somewhat similar in their end-to-end DApp experience to the settlement finality of the core. Another thing that I didn't have time to talk about, and I'm going to mention just briefly, is that if you noticed, the ingestion piece and the consensus piece are sort of two different distributed systems. They are different because we started like that. We started with Sui being this Frankenstein of ingestion and ordering protocols being very different. If you look at our code base, the API surface between the two is very small. However, that means that we are not particularly efficient. The same transaction is sent multiple times, first during the ingestion phase and then during the consensus phase. And we're going to fix it. We're going to merge both the ingestion and ordering into one giant Mysticeti to rule them all. And this is something that is mentioned in the paper as well. Now, in terms of the rollout, we are planning to roll out Consensus 2.0 to public testnet in April, May. We are going to run it in a very special manner where each other day we are going to flip between Consensus 1.0 and Consensus 2.0. This way, we verify that we can flick back and forth. We can verify that we are soaking properly Consensus 1.0, and Consensus 2.0 gives us enough signal on public testnet. If everything goes well, then the mainnet will go in June, July. And after that, we will start working on the integration of the injection phase into the Mysticeti, and that will happen in H2. I think that concludes the talk. Thank you very much.